All right, so if you got all those answers right, then great. You're probably already pretty effective at using Git. But if not, that's perfectly fine. As I mentioned, the goal for today's session is to uh, teach you a little bit about the best practices for Git so that you can be a little bit more comfortable and capable with using Git on ZOS. All right, so today we're going to walk you through quite a bit of material. Most of it is technical, but I'll start off with the basics. I'll give you an overview of Git itself, things like encodings, how you can ignore files, how you can handle merges and branching. We'll also cover some of the more advanced tools, like using Git merge tool to be able to merge multiple branches into one, using Git blame, Git bisect, which is a really great tool for being able to identify the culprit commit when you introduce a regression, and a couple of other tools as well. We'll also cover some of the UI tools that we can actually run on the ZOS terminal, including LazyGit, Tig, and GitHub CLI. And then we'll cover some of the best practices that myself and some of my colleagues use with respect to Git, including performance considerations and a whole lot more. And then we'll end it off with some of the GitHub essentials, so how you create pull requests and some of the other add-ons on top of GitHub that you can take advantage of. Okay, so for those of you who may be new to Git, I just wanted to quickly recap some of the fundamentals. So the first question is, what is Git? So Git itself is a distributed virtual control system. If you ever used SVN or CVS, it's very similar. You can really think of it as a tracker for your project files. It records every single change that you've made over time. And Git has really become the de facto standard source control tool for code collaboration. In the last decade, essentially every single developer has taken advantage of Git in some form. According to a Stack Overflow survey, about 94% of developers are using Git for their source control. And it's really a tool that allows multiple people to work on the same project without stepping over each other's toes. So just a couple of core concepts that we're going to be referring today. The first and main one that I will be mentioning multiple times is repository. So repository you can think of as a project folder that Git is tracking. And then we have the working tree. And the working tree is really a copy or a local checkout of the repository or project files that you can use to actively edit. Typically, you would do this on your workstation if you're using something like VS Code to check out your Git repository, or on your ZOS system. A commit you can think of as a snapshot or a save point, so it captures all the changes that you've made at a specific moment. And a branch is essentially an independent line of development, so you can have multiple work streams. For example, person A could be working on feature A, and then another person could be working on feature B. These will be implemented in multiple branches, and then you could also have a main development branch that integrates all of these together. And a merge is essentially the concept of integrating multiple branches into one branch, or combining multiple changes into one branch. A head is the reference point to a commit, and typically this is the current branch or the top level branch commit. So these are some of the core concepts that we're going to be referring to today, and if you're new to Git, I think experience really is what will help you understand some of these concepts. And the other question that I often get is, what is GitHub? So GitHub itself is essentially a Git server. It's hosted on the cloud, and it's a way for you to store Git repositories remotely. So you can think of it more as a front-end hosting service for Git. Okay, so then the next question is, how do I get Git? So on ZOS, there's quite a few different ways in getting it. I'll recommend two here. So the first one is through IBM's Open Enterprise Foundation for ZOS products. So if you're not aware of this, this is an IBM-supported offering. It's currently a bypassable requisite for ZOS 3.1 and above. It has all of your essential DevOps tools, including Bash, curl, and Vim. All of these are designed to help modernize the operating system. So if you need official IBM support, this is really the way to go. And second, we have the zopen community port of Git. So if you're not familiar with the zopen community, it's an open source initiative designed to port many of the open source or popular open source tools to ZOS. We currently have over 300 open source projects that we've ported, and it continues to grow. Git is one such project. So if you're looking for, the latest versions of Git, and perhaps some of the more experimental features that are being added to Git, then this is really the way to go. But if you're looking for support from IBM, then I would recommend IBM Open Enterprise Foundation for ZOS. And Rocket Software also does provide its own version of Git as well. Okay, so today's session is all about effective strategies in using Git. But before I dive into that, I just wanted to basically recap some of the Git fundamentals and basic Git workflows. So it all starts with working with a remote repository, whether it's on GitHub or GitLab. So for example, in the browser, I'm now showing you a GitHub repo for Vim. Vim is an editor on the terminal. And as I mentioned, these GitHub repositories are essentially project directories that host source code, but they don't necessarily just have to host source code, they can host all sorts of projects. And essentially the way it works is you will start by cloning a repository, whether it's on GitHub or GitLab, like what I showed you, and you would clone it onto your system of choice. Typically I work on ZOS, so I'm using the git clone operation on my ZOS system to clone the repo. And once you've cloned it, you can make your changes, and then these are typically untracked changes. And if you want to stage them and make them available in your Git local workspace, you would use the git add command. And then you can commit it to your current branch using the git commit command. So git commit, as mentioned, this records all the changes that you made as part of your project history. And then if you wanted to share your work back to the GitHub repo, you would use git push. And if you wanted to pull down changes, let's say somebody else has made changes to the remote repo, you would use git pull. To check the current status of your working directory, you would use git status. And then to view the project history, you would use git log. So just for demonstration purposes, we'll take a look at this Vim repository. Again, this has all the source code for the Vim editor. And the first thing you'll need to do is to grab the URL to the Git repo. So there's really two forms that I typically use. One is HTTPS and the other is SSH. I typically use SSH because it's a little bit easier to work with, especially if you want to contribute changes back. And this requires an SSH key to be created on your system. Okay, so right now I'm showing my terminal, and I will demonstrate some of the commands that we talked about. So the first one is git clone. I am on a ZOS system here, and I will be cloning Vim directly to the ZOS system. Oh, so I've already cloned it just before this, so I'll remove that. So now it's in the process of creating a local workspace. So as I mentioned, a local workspace is just a copy of the repository contents, and they're now hosted on my ZOS system after this clone is completed. All right, so now the copy has been made on my ZOS system. I can type in all the commands that I've just shown you, including git log, which gives you a history of all the commits that have been made up to the point. By default, the way GitHub and Git usually work is that it would clone the current or default branch onto your system. And that's typically either the master branch or main branch, and we'll talk a little bit about that later. Now, if I wanted to see if there's any untracked files or changes that have been made to my repo, I can type in git status. So let's say I modify one of the files in the Vim repository, say this is Vim, so I'm introducing a new line. If I type in git status, you can see that we have one file that's been detected as modified, and this is untracked. And now we can go ahead and add it. We can also check the differences by typing in git def followed by head, and then this shows me all the changes that I've made to my repository. So this is really a great way to summarize all the changes that I've made so far. And then if I wanted to create a commit, I can type in git commit. And this typically requires a new message to be added. And then now if I type in git log, you'll see that my commit has been added to the history. And now if I had a write permission to the GitHub repo for Vim, I can type in git push, but since I'm not a maintainer of Vim, typically the process is that I would create a fork, and I'll talk a little bit about what forks and branches mean. And then subsequently, I would go ahead and create a pull request to have that change merged in. Okay, so hopefully that gives you a bit of a summary of how Git itself works. But today we're going to talk a little bit more about some of the effective strategies and more advanced topics about Git. So the first topic that I wanted to talk to you about is specific to ZOS. So one thing that's really critical with respect to ZOS is being able to handle different types of encodings. So for some background, Git internally stores all of its files in UTF-8 format, but as most of you probably know, many ZOS projects, including COBOL applications or PL1 applications, use EBCDIC encodings like IBM 1047. So to be able to bridge this gap, Git supports what is known as a working tree encoding, and this is typically defined through a .git attributes file. So if you want Git to automatically convert from its internal encoding of UTF-8 to the local workspace encoding, you would need to create a .git attributes file, which essentially tells Git how to convert each of the files. So what it uses is a wildcard to detect, for such files that match this wildcard, convert them to this target encoding. And the way it works is the bottom lines essentially win out the top line. So if you have a wildcard that matches everything, and then you wanted specific encodings for specific files, then you would have them listed at the bottom in a similar fashion to what I have here. So just for demonstration purposes, I'll take you through one example project that I've created called EBCDIC project. This is in my own GitHub personal workspace, and I'll grab this. Okay, so we'll go through the same process of cloning this project on my ZOS system. The first thing I'll show you is the Git attributes file. So again, this is very similar to what I showed you on the slide. We have at the very top wildcard matching everything, and we're telling it to set the working tree encoding to ISO 8859-1, which is essentially ASCII. And then we have a couple of other files, including this EBCDIC file, which we're telling it to encode as IBM 1047. And one of the things that we've added to Git on ZOS is also the a feature to auto tag the files to that appropriate encoding. So as you may know, ZOS supports this notion of file tags, and we've extended Git on ZOS to support that. So now if I type in ls-lt, so T dash capital T will show you all the tags associated with each of the files. And you'll notice that the tags match the .git attributes. So as one example, we can take a look at this EBCDIC file. I'll use Vim, which is an editor on ZOS. It's open source. And you can see it's readable. And just to confirm, we can use the XXD utility. And you can see that all of the bytes are in fact in IBM 1047. So if you're dealing with IBM 1047 or encodings that are not the Git internal encoding like UTF-8, then we do recommend that you create a .git attributes file. Okay, so moving on, another common question that we get, which is very specific to ZOS, this is typically coming from newcomers who may have knowledge of ZOS, but newcomers to Git. And the question is, does Git support data sets? So the short answer is no, but there are a couple of ways in which you can continue to work with data sets. So two options presented here. The first one is with regards to IBM DBB's migrate.sh tool. So the first idea is you would use a tool such as migrate.sh to migrate all of your data sets into ZOS Unix files. So the migrate.sh tool itself handles a lot of the intricacies with respect to migrating data sets to ZOS, like tagging files, handling the encoding conversions for you. So it's really a great tool to do a one-off conversion, but you can also do the reverse operation as well. And the second option is to use a tool such as Ziggy. This is open source, and it's available as a ZOS ISPF Git interface, and I believe this also lets you work with data sets directly. But if you're looking to modernize your DevOps environment, then I strongly recommend option one, as you can take advantage of a lot of the complementary open source tools for Git, such as Git LFS and many others. But if you're keen to stay on ISPF and you don't really want to change your existing environment, then I do recommend Ziggy as it is a great option. Okay, so that's a little bit of the ZOS details out of the way. Now I wanted to talk a little bit about some of the gotchas and important things about Git. So first we'll start off with the git ignore file. So if you're not aware of what the git ignore file is, it's essentially a file that tells Git which files or folders to completely ignore. And while this may not sound important if you're working on a project where you're compiling a lot of source code and generating executables, you typically do not want to add such generated files into your repository. So this is where a git ignore file comes in handy. It essentially uses patterns or wildcards to tell Git which files to ignore. So there's actually one useful tip, and that is that through the zopen community, we have a project called Git Extras that we've made available, and this also provides a tool or command called git ignore, git space ignore, and it can automatically generate git ignore files for you, but also provides additional checks on top of that. So if I go back to the episodic project, and let's say I generated an A.O file. If I type in git status, you can see that it's an untracked file. But if I wanted to ignore it, I can create a .git ignore file, type in star.o, and now if I type in git status, you'll notice that it's no longer visible in git status, so it's being completely ignored. So this is just a great way for you to filter out any files that may be generated automatically through a build or some other mechanism. Okay, so the next thing that I wanted to talk to you about is branches and how you can structure them. So there's a few common types of branches that you'll encounter within a repository. The first and most common one is the main branch, also known as the master branch, which we saw with Vim. And you can think of this as more of your stable or production-ready code base. And then on top of that, you typically would discover these feature branches. So these are essentially branches that allow you to create a new feature or implement a bug fix. And they're typically isolated from the main branch. So let's say developer A was working on a new feature for Vim, they would create a new branch to help maintain and upkeep that feature. And then the idea is that once that feature has been implemented, you would go in and merge it back to the main or master branch. And then another common branching structure is what is known as release branches. So these are typically helpful, like if you're preparing a brand new release. So let's say Vim 9.2 is in the process of getting released. You would cut it off from your main branch, which may continue to evolve, but you want to keep your release branch more stable. So the idea is that you would create a special branch for that upcoming release. So many open source communities, such as Vim, even Git itself, follow this structured approach. And it's really just a way to keep a lot of your branches clean and focused on the specific task for that particular branch. So another aspect that's related to this is the concept of forking, and this is more of a concept related to GitHub. So the idea here is that typically if you're working with an open source project, you don't necessarily have write access to it, but with open source, the whole idea is being able to collaborate and contribute changes. So the idea here is that you would use a fork to create your own personal copy of another repository, and this fork would typically be stored in another account. But you would still use the same techniques for branching. You would create a new branch for your feature, and then have that essentially merged in at some point through a pull request. So just as an example, if I wanted to create a fork of Vim, on GitHub, they make it really easy. You can just actually go to the website in the repo for a particular open source project or project that you're working on, and then click on fork. Then you can choose the ID in which you would like to create that fork. I already have a fork for Vim, but essentially I would click on this and then click on create fork, and it will create a fork under my ID. I can then write to it. I can use the git push command to write to it. And then when I'm all said and done, I can create a pull request, which is essentially me asking the community to merge my changes with their changes. And you can see in the Vim open source community, they already have many different pull requests that are currently outstanding and need to be reviewed. And here's just a couple of examples of the pull requests. Typically, you would have a description of the changes that you've made, followed by all the changes that have been made for that particular merge request or pull request. Okay, so the next thing I want to talk about is something that can seem a little bit scary, but is really one of the most important aspects of working with Git, and that is handling merge conflicts. So conflict itself occurs when you attempt to merge two branches into one branch, but you're modifying the same line for the same file, but in a different way. So Git doesn't know which version is correct, so it will stop and it will ask you, the person who is attempting the merge, to resolve it. The way Git does this is it will mark all the problematic areas in the file with these markers, followed by, so essentially all the branches, all the changes that you made for your branch, followed by all the changes that have been made for the target branch, and then you need to manually go in and resolve this. So typically this involves editing the file and removing the markers, and then using git add to add it to staging, and then you would, if you're using the git merge command to merge, you would type in git merge continue until you've resolved all of your merge conflicts. So typically what we recommend, or what I've noticed from historical experience, is that if you want to reduce the number of conflicts in your project, it's really advised to try to promote smaller commits. So if your commits are smaller, then the likelihood of introducing merge conflicts is reduced. And one tool that I wanted to show you, so that mechanism of manually going in and merging or handling merge conflicts is manual and maybe not the best approach. What I recommend is using a tool called Git merge tool. So this is also provided through Git itself. And essentially this gives you an external visual tool. So typically, like if you're used to Vim diff or kdiff, you can actually choose which diff editor that you would like to use, and then you can use this more interactive terminal UI type of approach for handling your merge conflicts. So if we go in here and edit one of our files, so let's say we'll take this conflict.txt file as an example. Let's say I decided to add these dashes. Okay, and then what I'll do is I'll add this in to the staging area, and then I'll commit it. Add a dashes. Okay, so this is all fine and good, but let's assume that somebody else came in and made a similar change to this file, conflict.txt, and instead of adding dashes, they added quite a few equal signs. And what we're going to do here is we'll just directly merge this in, so that this is assuming that somebody else came in and modified this file, but in a different way. Now if I type in git pull, so this synchronizes my local workspace with what's in remote, it will detect that this conflict.txt file has also been modified, and it will notify me of conflicts. So right now it's telling us that conflict.txt has a conflict. And if we edit this file, we'll notice the markers are present, so it detected a conflict in line number 1. So this is what's in the remote branch, and this is what's currently in my local workspace. So now if I wanted to modify this and get it working, I can go ahead and choose which line I prefer. So in my case, I might prefer the line that I introduced. So I can go ahead and save it, and then I would type in git add conflict to add to the staging area, and then git commit to create a new commit. Or I can type in git rebase continue, and that will automatically adjust the commit for me. So the tool that I wanted to show you that would help with this, obviously this particular conflict is not as complex, but typically when you're dealing with source code, you have multiple lines and potentially multiple conflicts that you have to deal with. A git merge tool is the tool that I typically use for this. So on the left-hand side, you can see the remote changes, and this is what it was before, and this is what it was with my change. So I can go ahead and make the modifications through here, and it's a little bit easier to visually see what all the differences were through this editor. And again, you can customize this to any diff editor of your choice. Okay, so the next thing that I wanted to talk to you about is how you can integrate changes from one branch into another. And typically there's two approaches that are used, either merge or rebase. So git merge is probably the more straightforward approach, and maybe even more common approach. It takes the histories of two branches, and then it joins them together, and it creates a special merge commit to tie them up. And essentially what it does is it preserves the exact history of what happened, so it doesn't rewrite any of the history. And this is typically more important when you're dealing with main production branch and you don't want to change the history. Git rebase, on the other hand, is a little bit different. It takes your commits and essentially replays them on top of each other, or on top of the latest commit from the target branch. And this creates what I would say a more linear or cleaner history without any extra merge commits. So git rebase is really great for local cleanup before you're sharing. I typically use it when I'm working on a feature branch, because a feature branch is typically worked on by one person, so it's okay if you're rewriting your own history. And it just makes things a little bit cleaner when you eventually create that pull request that goes back into the main or production branch. Okay, so the next thing that I wanted to talk to you about is tagging. So tags are supported by Git as well as GitHub. And you can think of tags as permanent bookmarks for important commits in your project's history. Typically, they're used to mark releases or significant milestones. So as you can see here with Git uses tags for each of its releases. And creating a tag is really straightforward. You would just use the git tag command followed by the name of your tag. Typically, names of tags follow semantic versioning. So in this case, git tag followed by v1.0. Typically it's referring to the version of your commit. And if you wanted to share these tags remotely to GitHub, you would use git push origin, and this pushes them directly to your GitHub repo or GitLab repository. So by default, tags are not pushed. So if you type in, this is a common mistake that most people encounter, that is if you type in git push to commit your commits, or push your commits remotely, the tags are actually not pushed unless you provide an additional command such as this, or if you add in an extra option when you're pushing your commit. We do recommend that you use annotated tags. So this is really important just to describe what is included in your release. And you can use git tag -m to annotate it. So that's essentially the concept of git tags. And if I take you through Vim, so if you go to the GitHub location for a repository, typically you would see all the branches listed. But then in a follow-on tab, there is a thing called tags, and this is where you can see all of the tags or releases for your particular project. So if I wanted to get the snapshot of Git 1.876, I could click on this. And you could also even clone a particular tagged version of Vim, or even a branch of Vim directly on the command line. Okay, so now I wanted to take you through some of the handy tools that I take advantage of and I find really useful when I'm working with projects that are based on Git. So the first one we have is git grep. This is really a handy tool for being able to search directly within files tracked by Git. So its basic use is really simple. You can use git grep by the text followed by the text that you're searching for. So in this case, git grep followed by the function name. And the key advantage here is that especially in large repositories, git grep can be a lot faster than just using grep-r. And I use it quite often. I also use it in tandem with git jump diff. So if I wanted to jump directly to a particular file that has a source token, then I can use git jump and combine that with my grep query. So if I go into the Vim directory and I type in git grep followed by Vim, you can see that it's almost instantaneous, right? So the one benefit here with Git is that it has essentially every file indexed, so it doesn't actually have to search through the file system, and the results come back almost instantaneously. And you can see that it's listed all the files that have the token Vim, and also highlighted all the instances that are found with the token Vim. Okay, another useful tool that I often use is git blame. So this is one of the initial quiz questions. So this again shows you who last modified each line in a given file, and also tells you in which commit that this line was modified. So this is a great way for you to identify the reasoning for so let's say a new source code was introduced. You can understand why that was introduced by using git blame and then working backwards. So in the case of Vim, if we type in git blame followed by, let's choose a random file, txt in this case, you can see that when we introduced the line "this is Vim," it attributed it to me as well as the commit. But I can go through this file and then understand which commit introduced which change, and this is really useful if you're debugging a source file and you need to understand why a certain feature or implementation was added. Then if you wanted to view the details of that particular commit, you can get the SHA-1 ID here, and then type in git show, followed by that, and then this will tell you specifically what changes were made for that particular commit so that you can get a better understanding. So I also want to talk to you about git bisect. So this is really a lifesaver, especially when you're dealing with regressions. I often use it if I've encountered a regression and I know it worked in an earlier release. So its purpose is really simple but powerful. It helps you to efficiently find the exact commit that introduced the bug in your code base. And the way it works is it uses a binary search that searches through your commit history. And you can start by telling it the one commit that you know was definitely broken with git bisect bad, and then the one commit where you know things were definitely working with git bisect good. And then you would give it a test script that would run whatever test that you know would either fail or pass. And then you would type in git bisect start, and it would go through the process of using binary search to identify the culprit commit. So this is a really great way to quickly identify which commit introduced a regression. So a couple of other tools that I find handy. I already showed you git diff, but it shows you the differences between different states of your branch or commit history. I often use it to create patches. So the one cool thing about git diff is that it will show you the changes in a format in which you can actually apply through the patch command or through git apply. So you can use git diff and redirect it to a patch. And then let's say you have another local workspace, you can use git apply followed by the patch to apply it to that workspace. Git reset is another one that I use often. So let's say I may have corrupted my workspace or made a change that I didn't intend to. I can use git reset to essentially move the current head position or even completely reset my local workspace to another SHA-1 commit or branch. Then there's also git revert. So this is more of a safer way to undo a previous commit or change. So instead of deleting everything in your workspace, it creates a new commit that's essentially the opposite of the changes that you've introduced. And this retains the history of your project without having to essentially rewrite your history. And then another one that I often use, especially if I'm working on a feature branch or maybe a new release branch, is a git cherry pick. So this lets you grab a specific commit from one branch and then apply it to another branch. So this is often useful if you're working on let's say like a new release branch, but you don't necessarily want all the production changes that are going in. Maybe you want to cherry pick some of the changes for your release branch that you think would be useful for that release. Okay, so the next thing I'll take you through quickly is performance optimization with regards to Git. So some projects within Git can be really, really big, and that can have an impact on the clone time with respect to downloading all the source code onto your system. So the big thing that can help influence performance is how much of the history that you're really interested in. So instead of downloading the entire project history, a common thing that's being done in CI/CD pipelines is to do a shallow clone, and this means that you're only downloading a specific number of the recent commits. So one of the main benefits here is that you're going to get faster downloads and also less this storage. So instead of retaining all of the history for each of the files, you can tell it specifically, I just want to retain the last commit. This is really useful if you're doing CI/CD type of pipeline workflows where you just need the latest commit, right? Because you're potentially just building the source code and you don't necessarily need the entire history along with your project repo. So the way to do this is to pass in the --depth option. So you can pass in git clone followed by --depth, and the number would specify how much of the history that you want. And this can have a huge impact on your git clone times. So for example, I think with Perl, by default, it takes about a minute or two to clone the entire project with all the history. But if you use git clone followed by --depth, of 1, for example, it will reduce that down to about 4 or 5 seconds, based on when I last tried it. So it can have a huge influence on the performance of your Git clones. And then here's just a couple of more advanced topics. So let's say you're also storing in large files or binaries in your Git repository. Another way to avoid downloading them is through something that is known as partial clones. And essentially what it involves is for you to pass in this -- filter option. And it supports multiple sub-options, but a common one is blob followed by none, which means that you want to omit all of the large binaries in your repository. So this can also have a big influence on the performance and also the size of your local workspace. Sparse checkouts. So this is also very useful if you're dealing with a ton of files, but you only want to have specific folders in that repository. So sparse checkouts is a common approach to that. It won't necessarily improve the performance, but it does reduce the overall space that's being used. Submodules. So this is not really related to performance, but related to how you would structure your repositories. So let's say you have a repository like Vim, but perhaps Vim depends on another repository. Let's take, for example, X11. So there's two approaches. So one approach is that you can have the Vim build process dynamically clone X11 during the build process, or you could have what is known as a submodule that refers to the X11 repository. So you can think of submodules as symbolic links, just like in your ZOS Unix file system, where symbolic links point to other directories, create shortcuts for you. Submodules are essentially like symbolic links to other repositories. And you can add a submodule very easily with git submodule add followed by the repo. And then one thing to keep in mind is that when you're cloning a repository that has submodules, you would need to pass in the -- recurse submodules option, and this will recursively clone all the submodules within your repo. Right, so Roland, how are we looking with time?
We're at time.
I think we're up in time. It's 11 o'clock, so. Do you want to do a 30-second wrap up and then?
Yeah, absolutely. So I do have quite a few other topics that I want to discuss, but we'll make these slides available. We do encourage you also to customize your Git configs. If you're dealing with commits that are in open source, we do also encourage you to sign your commits. This is more of a way to make sure that all of your changes are done in a secure fashion and can be trusted. And then one thing that I didn't get a chance to show you is the UI tools. So there's quite a few to choose from, but I would recommend LazyGit. This is a way to just browse through your local workspace in more of a interactive fashion. And unfortunately, we didn't get a chance to go through some of the GitHub aspects, but we will make these slides available, and hopefully you can take these into account when you're dealing with Git and GitHub in the future. But I do have a couple of reference slides in here that you can take a look at with a lot of the material that I talked about today. And if you have time for questions, then feel free to ask.
So thank you. Does anybody have any questions? If you want to stay behind, you can still do it. If not, then any questions? It's a lot of information. Okay, thank you so much for coming. Hopefully it will be useful to you.